episode of the Klingberg Wing Mark II development. I'm Rob Klingberg, your host. I haven't spoken to you guys in a while. I put up some videos. You've probably looked at them, wonder what the heck's going on. I've been very busy trying to straighten out some aerodynamic issues on the wing. If you've watched the videos, you see a couple of short flights at El Mirage. I take off, I kind of flounder through the air, and then I have rough arrival back on the ground. And the issue is that I'm having non-linear control effect on the stick. I push it a little bit, I get some effect. I push it more, I get more. I push it a lot more, I get none or less. And you cannot fly an aircraft accurately if the controls are non-linear. So there's a flow separation problem that's occurring on the Elevons. And I'm here today to talk about that, what's causing it, what the potential fixes are, and how I'm going to move forward. So, first of all, let me explain to you that on any control surface, and let me fudge this a bit, I hope you can still see it. Generally speaking, on whether it's an elevator or a rudder, aileron, Elevons, you're going to get about 16, 17 degrees of deflection before the flow starts to separate off of the control surface. And there's a variety of methods that are used to increase that to a higher angle so that you get more control effectiveness. And most of those methods would get you up around 22 to 25 degrees of deflection, which is more down here like this. And then when you see aircraft fly with these huge deflections, aerobatic aircraft and so forth, well, the flow is just detached from the control surface, and it's really the flow runs into the underside in this particular case. It's deflected down, and the flow on top is just coming off like this, unless they have some kind of fancy slat set up or something like that. So on modern sailplanes with laminar flow airfoils, this is quite an issue because the laminar flow just comes back nice and smooth and just shoots off, and you can move the control surface wherever you want. Not much happens. So they have trip strips that they put on sometimes right in front of the hinge line. I have some here, a particular version of it. I don't know if you can see it. It's clear plastic, very hard to see. Maybe if I peel it off of here, there, you can get a look at it that way. And I've tried these on my wing here, and they have no effect because they're very thin. Laminar boundary layers are very thin. That would work in a laminar boundary layer. This is a turbulent boundary layer. It's quite thick, and it just goes right over the top of those vortex generators, and nothing happens. So I didn't realize this was going to be as much of a problem as it is, because this airfoil that I chose, the NACA 23015 series, actually 230 series, and I have 23015 at the root, 23012 out at the tip, naturally have a transition from laminar to turbulent boundary layer at about quarter chord or 1/3 a chord. That's not happening in this particular case on this wing. I built a really clean wing, composite up front, very smooth, no steps, no bumps, no nothing, and the flow staying laminar all the way back to about 60% a chord because the Reynolds number is so low. This airfoil is designed for Reynolds numbers of 1 million and up, and at takeoff and stall speed, this wing's operating about 400,000. So the flow is just kind of glued to the wing. The drawback to that is when you deflect the control surface, it doesn't go with the control surface. It just goes off straight. The momentum carries it right straight the way that it was headed. It has no desire to stick to the wing. The viscous forces are too low to keep the flow attached. So what can we do about that? What we've been working on all along is to cause the Elevon to be taller. The leading edge, and I'll pull it out here, we want the leading edge, this leading edge of the Elevon, to be taller than the trailing edge of the wing. So it sticks up slightly above it. And this causes the flow to accelerate and go up over that hump, and that helps it stay attached. And you can get up around 22 degrees of deflection that way. So what I did here recently on this wing, the left wing, I moved the hinge line aft and moved the whole Elevon aft, so that when it rotates, and I'm going to have to kind of fudge this, and maybe you'll see, maybe you won't. I'll put up a still picture here with this also so you can see it. But in a neutral position, the surfaces are flush, and when you deflect it, I disconnected the one hinge, it sticks up like this. And this is a common trick, and that type of hinging was used in World War II in a lot of fighter aircraft and so forth. So the flow comes back here, up over the hump, and sticks to the control surface. Well, that works fine if you're flying fast. If you're flying slow, we were testing it a couple days ago, not much happens. Very interesting. Getting about 17 degrees of deflection, and that's it. Flow starts to separate. Once the flow starts to separate, you really don't have any more control effectiveness. So it's kind of a bad thing. And Peter all along had said, hey, Raul, I hate to say it, but maybe the correct answer is vortex generators. And he's right. That is an answer. It increases the drag, but it will for sure cause a turbulent boundary layer, and that turbulent boundary layer will stay attached to the control surface much longer. So I made up some just junky little vortex generators here, and we played around with these. And when we had them about 3 or 4 inches in front of the hinge line, peaches, worked really good. Turbulates the flow, got a nice turbulent boundary layer, stays stuck to the Elevon up to about 22, 23 degrees of deflection of the Elevon, which is what we want. Most aircraft should be flyable with 20 degrees of Elevon deflection or aileron or whatever control surface you want to talk about. That 20 degrees should be enough. That generally Elevons are sized to create a certain rolling moment, and once you size them that large, you're really only using 3, 5 degrees of deflection, 10 at the most. 20 would be when you're in severe turbulence and you're trying to maintain control of the aircraft, or you have some weird thing on takeoff and it's very low speed and you're having to use big control throws. What I was getting into with the flow separation is I would deflect the Elevons as needed, in some cases down, and you can go look at some videos where you can see the tufts where we're towing at El Mirage, and you see me go into some down elevator, and then you see the Elevon go down even more, and that's because I'm a little bit out of trim, and I'm putting in right stick, which is putting the left Elevon down, and so I got the tow ropes pulling the nose up, it wants to roll left, so I'm rolling right, so I have maximum deflection on the Elevon down. It's like 30, 35 degrees, the flow's all separated, and I lose control of the aircraft. Bring the Elevon back up to somewhere around 15 degrees, flow reattaches, I have control effectiveness again, but I don't have enough authority to cause the aircraft to do what I want it to do. And just because controls are effective doesn't mean you have sufficient authority, which is the power of the controls to move the aircraft. And usually you size the Elevons to generate sufficient rolling moment so that you have enough power to control the aircraft. I did not do that for this design. I skipped the part where you calculate how big do the Elevons have to be. I did that for 2 reasons. Number one and foremost is I wanted to do this reverse taper Elevon that's inboard of the winglet to investigate preventing stalls and spins. That was very important to me, and no matter what answer came out of X-Foil on how big this Elevon should be, I was going to make it this size because I knew that this would work for preventing stall spin accidents. I tested this significantly on a series of models, and it works wonderfully. They are essentially spin-proof. And lo and behold, I've stalled this aircraft probably 4 times now in flight, and it never drops a wing. The reverse taper Elevon, the huge potential fence that the winglet represents, and the fact that the outboard section of the wing, everything from the winglet out, has no control surface on it. So it stays flying, the flow stays nice and straight, no spanwise flow, and you don't drop a wing when you stall, which is great. It's wonderful. The drawback is this Elevon's not big enough. It's not big enough by a fair amount. So because it's not large enough to try to control, get enough control in extreme situations, I'm deflecting it a very large amount, and then I lose control entirely. So the Elevon simply has to be bigger. We've got to get some trip strips on here to make sure we have turbulent boundary layer, and actually we need vortex generators. The little clear guys, those are trip strips. These are vortex generators. So we're going to have to incorporate some vortex generators on the wing, both inboard and outboard here. And I'm going to have to increase the size of the Elevon. Now, the reason I didn't want to put the Elevon outboard of the winglet is because when you deflect an Elevon up like this, well, the flow's coming back, it sees the Elevon, and it's a swept wing, and it goes, oh, it's much easier to just go this way. I'm just going to go spanwise. And when it goes spanwise, it drags all the flow with it, the boundary layer, everything else. And as you're dragging that flow out towards the wingtip, if you're near stall speed, that will actually cause the aircraft to stall prematurely, drop a wing, and go right into a spin. Span-wise flow is a big bugaboo on swept-flying wings. It's even a big problem on jet airliners. Those are essentially swept-flying wings with a tail and a big cigar tube on them. Anyway, so the question becomes, how much do I have to extend the Elevon? How much do I have to increase it in size? And what do I do with the winglet that is built into the structure here? It disassembles, but is it okay to leave it here, or do I need to move it outboard? Well, Peter did some runs on X-foil and found out that if we increase the chord of the Elevon here and keep this reverse taper, well, we're up to almost a spar up here by the time we have an Elevon large enough. And that's because it's quite a ways inboard. We have a lot of wing that's outboard with no control surface on it. So in order to make it fully effective, we have to increase it just too much in area. It's impractical to run all the way up to the spar. So be saying, you might be asking at this point, well, why were you so sure that these were going to work? Well, they worked on the models. And then I went back and watched the model videos, and I'll put up a picture from one here, and you can look at the tufts. And the Elevon's deflected like 30 degrees, 35 degrees, and those tufts are just glued to the Elevon. In hindsight, I just overlooked the simple fact that the model's flying totally laminar. And that's laminar flow that's just absolutely glued to the surface and taking the tufts with it. So this concept on the models works great. It does not work at this scale because we're in a weird Reynolds number region here, 400,000, 500,000, a very bad place to be. Weird things happen. Works this, you go a little bit this way, you get certain types of behavior. Go a little higher Reynolds number, you get completely different behavior. It is a difficult zone to operate in, but foot-launch rigid wings, they all operate in that zone sooner or later because of our stall speed so low and the amount of wing area that you need to fly, and you work it all out, and sooner or later you're going to fly through a zone where you got Reynolds numbers that are in the 500,000 range. So really the answer comes down to extend the Elevon outboard. Peter did runs showing that if I add 3 feet to the Elevon outboard, I will have plenty of control authority. I'll have plenty of control power, keeping the same hinge line here. And in those runs, he moved the winglets outboard. But then it becomes a question, is the remaining 30 inches or so, or 35 inches of wingtip with no control surface on it, is that enough to prevent the stall spin problems, to keep the flow locked in chord-wise, stop the span-wise flow? Don't know. This is an area I'm still experimenting in. I don't have any codes that would simulate that flow really well, and I don't have a supercomputer to run them on. And I'm working off of just my knowledge and assumptions. So the potential fence is supposed to help in that situation, and that's the winglet here. That helps stop the span-wise flow. So one would think that if I'm extending the Elevon and the Elevon causes span-wise flow when it's up, well then I'd want to move the winglet out with it. That's probably true. But what if the Elevon is only half of the span of the tip panel? Maybe that remaining portion is enough to keep the flow straight. I don't know. So we're going to have to do some tests to find out what will work and what won't work, and whether or not the winglet has to be moved or not. Because I can cut Elevons out of the wingtip panels and run a pin through here and just slave them off of the main Elevons, and they'll just move up and down together. That's an easy change. Cut a little slot here in the winglet mount, and everything would probably be just fine. And it would assemble and disassemble just as easily, and it wouldn't add much weight. So, but to cut up the tip panels, I got to strip all the covering off, got to cut all the ribs, got to cut the trailing edge, I got to put in 2 spars. It's a major modification. If I move the winglet outboard also, well, that's even a bigger modification, because I got to put in some kind of filler here in between the 2 wing sections, and I got to build some kind of mount for the winglet out there, and that's an even bigger deal. So my current plan here is to kludge my way through it, as we like to say here. Kludge or jerry rig or whatever you want to call it. It's just scummy down and dirty engineering. I can take some of my favorite material, this foam core board like this, and I can hinge it to the trailing edge of the tip panel. I can put 30 inches on there, 36 inches or whatever, and then build some type of U-shaped bracket that goes around the winglet mount here that will slide over this and slide over this so that when the Elevon goes up and down, it'll take this up and down with it. It's probably what I'm going to do. And for a little short hop at the beach, well, foam core's just fine. I don't have to build anything fancy. It's inexpensive, it's relatively lightweight, and then we throw it away when we're done. And I've used that a lot here as we test our way through this thing. That I can do without moving the winglet. We can look at the flow conditions, see what the tip is like, see if I get more control power, where I don't have to deflect the controls more than, say, 10 degrees to get control effectiveness on the aircraft, to get good solid control of it, good maneuverability. If we see a bunch of spanwise flow on the tip, well then we're going to have to go back and when I do the final modifications to extend the Elevon out into the tip panels, I'll have to move the winglet also. I don't know how that's going to come out at this point. So that's where it stands right now. It's going to be a while before you see any more videos or any other data coming out, because just to do this little change here, I have to put the hinge line, the Elevon, back where it was before. So I got some more cutting and drilling and some parts to make, so I can make this Elevon like the right wing, put it back the way I started with it. And I got to make up some. Maybe I won't make vortex generators. You know, you can buy them for cars. They get sticky back on them. Maybe I'll try those, and I can just buy a couple sets of them and stick them on the wing, see how they work, and that'll prevent having to do that building. And then I got to rig up some type of drive system here, and that's going to take some time to figure out what'll be just strong enough to take the control force loads and not be too heavy and easy to build. So all of that said, I knew going into this that I was taking the risk that this Elevon would not have sufficient control authority because I was working towards that goal of making a spin-proof flying wing. I achieved one goal and ran into the other challenge that I knew was a potential outcome of it all, and that's okay. That's kind of what experimental engineering is all about. And now I'll go and do more work to see if I can get both things working. And right now it looks like if I stretch the Elevon another 2 or 3 feet out into the tip, it'll work. And I'll have plenty of control authority. But now I'm up against some significant modifications. Part of the issue here is that I get for a low-speed aircraft, I get fairly early separation on the boundary layer off of the control surface when it's deflected. And the airfoil, like on the Swift, doesn't have that problem because they have a fully turbulent boundary layer. And this guy's supposed to have that turbulent boundary layer also, but doesn't because of its design and the low Reynolds number it's operating at. The Swift airfoil, much better designed for operating at low Reynolds number. So I'll need some type of vortex generators. And you might be asking, well, gee, Raul, why didn't you just put the Swift airfoil on your wing? And that's a very good question, valid question. And all of these things are trade-offs. There's no perfect airfoil for any aircraft or series of airfoils. They all have their pluses and minuses. Now, on the Swift, and I'll put up a picture here somewhere, you'll see that they do a really rapid pressure recovery after the maximum thickness point. That trips the boundary layer, makes it nice and turbulent all the way back. And when we went out and did measurements the other day and I put tufts on the Swift, darned if those tufts didn't line up just like the streamlines that are shown here in the drawing. So, accurate stuff. The Swift has a maximum CL of about 1.5, and so does this airfoil. They're pretty equivalent. Where they depart is in their shape. This is kind of a semi-symmetrical airfoil, and the mean camber line actually has a skosh of reflex in it. So, at all angles of attack from 0 up to stall, the pitching moment is 0, which is very handy on a flying wing. Therefore, I don't need as much washout to achieve stability with this wing as they need on the Swift. I think the Swift's got 10 or 12 degrees of washout. I think the Millennium might have 14, something like that. My wing, 8 or less. And that difference in washout means I have a much better high-speed end. I can go faster. The Swift really kind of tops out at 50, somewhere between 50 and 60 miles an hour. It's about as fast as you want to go in that aircraft. I had intentions of going much faster in this thing. So why did I choose this airfoil? Speed, baby. I want to go fast. This thing could probably easily hit 100 miles an hour. Whether the structure can withstand turbulence at that point remains to be seen, but it'll go fast. Because I have the big fantasy that, one day I would be the designer known for building the first foot-launch aircraft to fly 1,000 kilometers in a day. And this aircraft actually has that capability. We get the cockpit closed off and go fast. Might do it. And that'd be pretty incredible to have a foot-launch aircraft that can go that kind of distance in a day. It'd be a long day. So big dreams and a lot of work to get to them. And right now we have an aircraft that's not really flyable. In fact, it's a little scary to fly it. But that's okay. It's just me. And we'll safely move along and make changes until it is up and flying well and has good control authority. I know eventually this airfoil will work for me. Why? Because I had it on my first wing. These are the same airfoils that I used on my first wing. That wing had beautiful control authority, and you could fly it with 2 fingers. It was the best balanced controls I've had on any aircraft I've flown, and there's dozens and dozens of aircraft that I've flown. It was a beauty. It had its other problems, but controls, no, it wasn't a problem. So I know the airfoil will eventually work. We just need to get the Elevons sized correctly. So I ask you to hang in there with me, no pun intended. I know it's going to be a while before we get back out again, a month or 2 maybe, and nothing's going to be happening in the meantime except for me hacking away in the garage. But that's the name of the game when you're doing developmental engineering, and especially when you're pushing the limits and trying things that have never been done before. So it's an adventure no matter how you look at it. I'm glad you decided to join me on the adventure. Hope you're having fun. And in the meantime, as I always say, fly safe and bye for now.